Hello BC class. I just want to talk again about what we did in the earlier video. We came up with what a polynomial fit would be for any function, and in terms of a Maclaurin series or Taylor series centered at 0. So the only objective remaining that we have to finish up is I said that we were going to construct a polynomial series for any function, and I want to just complete that goal. So let's pick any old function. So we're going to use, let's say, we'll use a function and we'll say, let's try sine of x, or even cosine of x. Okay, so this will be the function that we want to model with a polynomial, and we'll center it at 1. So our Taylor or Maclaurin, we'll center this at 0. We'll consider the polynomial function as a summation of terms from of an infinite set of terms, and we'll see if we see a pattern develop. So it will be the nth derivative times the function at n. This should be the derivative at 0, since we're centering at 0, times the polynomial nth term all over n factorial. So let's get to constructing this. So our first term for the function is f of x is equal to cosine of x. And now we need the derivative. That'll be negative sine of x. And then we need the derivative of that, and that will be negative cosine of x. And we'll take the third derivative, and we'll see that's going to be the sine of x. And the fourth derivative is cosine of x. And the fifth derivative is negative sine of x. And we keep going through the pattern. Hopefully we'll see a pattern before we exhaust ourselves. So now let's evaluate these at 0. So f at 0 is equal to 1. That's because you plug 0 into the cosine function. F prime at 0 is the sine function at 0, which will be 0. F prime prime at 0 is the negative cosine function at 0, which is negative 1. The third derivative is equal to the sine function at 0, which is 0. And maybe you are starting to see the pattern. Which is positive 1. And now the fifth derivative at 0 is negative sine at 0, which is 0 again. So here are derivative terms. They go from 1, they go to 0, negative 1, 0, 1, 0, and you can assume that there's a pattern here. It's going to go negative 1, 0, 1, 0, and so on. So now that we know our derivatives at the centered value for the polynomial, we can start writing them out. So we're going to start writing them out. I'll just write the expanded form. So we have the 0 derivative at 0, which is just a function value. That's at x0, which is a 1 value, or 0 factorial. And we'll fill that in a second. And we have the first derivative at 0. X to the first power over 1 factorial, plus the second derivative at 0 over 2 factorial times x squared, and so on. And what you'll notice is, and what's amazing about these functions, is any function you have, it has a pattern associated with it, and you'll see in a second. And this is the exciting thing about the mathematics, is that you get to see this pattern. So watch, let's just plug in some of these. So the first term, I'll use a different color ink so it's easier to follow. The first term is going to be 1 over 0 factorial, which is 1, times x to 0, which is 1. So that term is 1. Plus 0 times x over 1 factorial. Well, that's just going to be 0. Plus, the next term is negative 1. So I'm going to put negative 1 in here. X squared over 2 factorial. Plus, guess what? The next term, it's 0. Let's look at the next one. Well, my next one is going to have to be the fourth derivative x to the fourth over 4 factorial, which is going to be plus the fourth will be 1 over x to the fourth over 4 factorial. So look, we can see the pattern that's going on. The function is going to be 1 plus, minus x squared over 2 factorial plus x to the fourth over 4 factorial. Guess what the next term is? It's minus x to the sixth over 6 factorial. Yeah, you got it. The next one is x to the eighth over 8 factorial. Isn't this amazing? The cosine function has a pattern. It definitely has a pattern. It's an even function. Notice, this is an even function. This is even. This is even. Even. It's all even. Amazing. So what we're going to do is we're going to try to write out the general term. So I'm just going to write it out again. X squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. Another thing that you should notice is that the signs are alternating. We want to write out the general term so we don't have to do this forever. So what we're going to do is we're going to consider this is the 0th term, the 1st, the 2nd, the 3rd, the 4th, and so on. And we're going to come up with a general term. It's going to be -1 to the nth, because if you raise -1 to the 0 power, that becomes 1, and it matches our first term. It's going to be x to the 2n, because each one, as you can see, as we go up in n value, our power goes up by twice what the n value is. And it's going to be all over 2n factorial. So what that means is now we have our general term for the sine function, and if we have that, we can also do some other things. So for example, this is the cosine function. If you remember, the derivative of cosine, or the integral of cosine, is sine. So now what we can do is, if you want to know what the sine function would be in terms of a power series, you just do term by term integration. So everybody, what's the integral of 1? You remember that. That's x. What's the integral of x squared? Well, you raise the power by 1, so it's x to the third. You put it over the new power, 3, and you multiply by 2 factorial. Well, guess what that is? That is 3 factorial, right? And then you go to the next term, and you're going to raise that power by 1, x to the fifth, put it over 5 times 4 factorial, and that becomes x to the fifth over 5 factorial. Look at the sign, it's changing also, just like the cosine function did. Minus, this is going to be x to the seventh over, I'm going to raise the power by 1, 7 factorial. You get to see the pattern, right? If you also notice, remember how I said the cosine function is an even function? Well, guess what the sine function is? It's odd. And we can do the same thing with the last term. We have -1 to the n power, and that's going to be x to the, we're going to raise 1 to that power, so we have 2n plus 1, and we want to divide by the new power, 2n plus 1 factorial. And now you see that you have the general term for the sine function. Hopefully this helps with understanding how we can take a simple Taylor series centered at 0. Remember that the series is the sum of well, here's a general term, and for any function, if you know its derivatives at its 0 value, you can write out its infinite series, it's a polynomial, and what you should notice is no matter what function you choose, we should get some sort of a pattern of polynomials. And that's one of the most interesting things about these different series that we can construct. I hope this video helps, and I look forward to talking again about another Taylor series expansion.